Okay, so we're doing section 6.6. This is similarity in transformations, and we're revisiting a topic way back in unit 1. It was first introduced. We were talking about similarity, and we're talking about now in transformations. If you remember, similarity is having the exact shape, but not necessarily having the same size, and not really having congruity. Right. So from today, we're gonna be able to map one similar object onto another similar object, and justify that the figures are similar, and describe a sequence of transformation uh, that map one image onto another pre-image, right? And then remember, we're talking that similarity is having the exact same shape, but not necessarily the same size. Go ahead and stop my video so you can see that. Yeah, okay, there we go. Yeah, so here we go. We're just talking about just having the same two different sizes. All right, so here we have two different polygons here. All right, obviously, they're not the same size. You know, they went underwent a dilation. Oh yeah, by the way, two figures are similar if and only if one underwent a dilation during the sequences of transformations. Okay, so the line segments distance is not going to be preserved, but the measures of the angles will be the same. So, but they won't be congruent, but they'll be similar. Okay, so here we have two different um, images of transformations. There's one over here on the left. This is the pre-image, and this is the image. And then one over right. Here on the right, this is the pre-image, and then this is the image. Right, and this one was, so we'll take a look here. If I had patty paper, I'd show you on with patty paper, but I don't. So I'm going to show you here. Obviously, this was dilated to make this, and something happened. This was rotated to make this one as well. So we'll go ahead and select this one. Now the question is this red imager similar to this black image? In order for that to be true, the all the lengths of the segments have to be have to share the same ratio. So first, let's rotate this image to be the same orientation, excuse me, of this image. So I'm gonna rotate this thing. I think let's go left. See if I rotate it right, if it's the same image. Nope, that's not right. Let's rotate that back left. Let's rotate that left again. Rotate that left. Okay, all right. Now it's oriented the correct way. All right, I'll move that, and now I got to see if that is if I have like a good ratio here of side lengths. Okay, so let me see now if I have. Let me count my change in x. Well, first, before I even see that, let me see if the angles are the same. If the angles are the same, then pretty much deduce that I'm going to have the same length ratios. So let me check this angle and this angle. Well, that angle and that angle line up pretty well. This angle and this angle, they line up pretty well. They're the same angle. This angle and this angle, they line up pretty well, and this angle and this angle, they line up very well. All right, well, so now let me go ahead and unclick off of this. I could click and see, well, this line segment, this is a 2 by 2, so it changes 2 left and 2 up. This is a change in 4 by 4, so that's a 2-to-1 ratio. This is a 1 over and a 4 up. this is a 2 over, and it's like a 1, 2, 3, 4, 5, 6, 7, 8 up. So that's a 2-to-1 ratio. Okay, and this is a 1, 1, 2, 3, 4, 5, 5 up. Count that again. Let me zoom in and see. So this is a 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. That's a 6 over, and a 1, 2, 3 up. That's 2-to-1. This is like a 1, 2, 3, 4 over, and a 1, 2, 2, 1, 2, 3, 4, and a 1, 2, 3 down. Okay, so that's a 4 over, 3 down, and this is a 1, 2, 3, 4, 5, 6, 7, 8 over, and a 1, 2, 3, 4, 5, 6 down. All right, so looks like those ratios have all checked out. So this was a dilation of a 2-to-1 scale factor, and a rotation left at 90 degrees. All right, cool. So there you go. So that's that one. So these are similar polygons. These are similar quadrilaterals. Okay. So there you go. So how about this one? These two. Okay. Well, let's see if these two have similarities. Let me go ahead and just orient this one. Let me go ahead and rotate this one left. Okay. And let me see if I can line up. Well, that doesn't line up. That one doesn't line up. But if that one was there, it wouldn't line up, and that one doesn't line up. So I'm not even gonna bother to try to figure out the ratios here because they're not going to be the same. The rise of the run aren't going to be the same to these. So I'm not going to bother because these are not similar ratios. So these are not similar polygons. So that's a pretty good example there between similar and not similar polygons there. Okay, so let me bring down a homework example here and show you what the example of homework looks like. So I guess I'll just grab this here, grab the whole game to grab this, put it on this. Yeah. All right, so here we go. When a sequence of transformations result in both angles and the sides of images are congruent to the corresponding, so this is both the angles and the sides are congruent. The sequence does not include dilation because the sides change during a dilation. The sides change during a dilation. That's the whole preserving distance thing, and dilations do not preserve distance. So if it does include a dilation, the corresponding if it blank includes dilation, the corresponding are congruent, and so it does include a dilation. The angles are congruent, and the sides are proportional, right? Because they do not maintain proportional side or congruent sides, but they're proportional, and the proportionality is the scale factor. Remember, the scale factor is a proportionality, right? So yeah, that's cool. Let's scale out and I'll show you. I'll prove it to you. Okay. So here is a dilation, right? This is a dilation of that. And let me go here and I'll show you. Right here is that oh, I need a smaller. I'm gonna just show you from J to M, right? This small distance here from J to M. This is a right triangle. Maybe it'd be a little bit bigger than that. J to M, that's a right triangle. And this is a right triangle from J to M as well. Okay, and if I wanted to figure out the distance from J to M, it would be the square root. This would be the square root of the distance of between my x and my y values squared, right? So the difference between 7 and 3 is 4 squared plus the difference between 6 and 2 is 4 squared, right? So that is 16 plus 16, and that is, oh, I can make up a calculator on here. Yeah, so 4 squared plus 4 squared equals, and I square root of that is that's some weird number, right? Square root of 32, square root of 32, square root of 32, right? But this doesn't get as easy as that, right? So square root of 32, that's 16 times 2, right? Because we do clear button. 32, well, that's 23. Let's see, 32 divided by 2 is 16, right? And that's a perfect square. That's 4 times the square root of 2. All right, that's 4 square root of 2. All right, so over here, so that's the length of this in radical terms. Isn't it a radical? Right, yeah. So anyway, so this is, let's see, 1.5. This is 3.5. So that is 2 squared. All right, and the distance of this is 1 and 3. That's plus 2 squared. 2 squared. All right, so that is 4 squared plus 4 squared, or is 4 plus 4 is 8. That is square root of 8. That's 2 square root of 2. So my scale factor on this one is my after 2 square root of 2 divided by my before, which is 4 square root of 2. 2 square root of 2 go away, and this is 2 divided by 4. My scale factor is 1/2. And I could do that anywhere, right? Or I could have been really, really easy, right? So these are my sides are proportional. The length of my sides are proportional to the scale factor. So this is the scale factor, but I could also figure out the scale factor by seeing my change in x, my change in x, or my change in y, a change in x, right, of my points, right? So actually my change in x is, so my x value of my let's see. So my x value of my j is -3. -3. That's my x value of my j. -3. My x value of my j prime. This is my before. My after is 1.5, and that's going to be 1/2. Okay, so my x value is 1/2. So it underwent a reflection and then it shrank. So this is what happened first. So it's 1/2. So it's negative 1/2, but it want to reflection first. That's why it's like that, right? So it so yeah, it's still 1/2 the size. And you could do the y. The 1/2 would go away if I did the y value. So my y value initially was afterwards was 3. My y value after was 3. My after y value equals 3. And then my before y value equals 6. It's 1/2. So this scale factor of 1/2. So all going up with my J point. Up my J point there. Now you could have done it off of your K point if you wanted to. 3 and 1/2. You could have done it for your L point. 1 and 1/2. Or that M point. 2 and 1 and 2. Right? Either one of them, it would have worked. Right? But see, your scale factor is 1/2. All of your line segments, 1/2. So that's just to prove my point. Didn't have to do that. That was just showing you guys that that is true. Okay. Right. So write the sequence of the pre-image onto the image. Let's go clean this all up a little bit here. Dig this up a little bit. Oh, this is things I'm going to get it. Okay. All right. So my sequence of transformations. Well, the first sequence, like I said, it was a reflection, right? Because you can see here that it is flipped over one side, right? And then it shrank, or you could have shrank it and then flipped it. Either way, this is one of those commutative ones. So this is a could have been a, I'm gonna type it. This is write a sequence. So this is a reflection. Wow, that's big. Let's make that like 10. Reflection across y axis, then a dilation of scale factor equals k equals 1/2, then about origin, or the opposite. And then you could write the algebraic expressions. So algebraic expression for reflection is x comma y. Reflection is across the x-axis, x, y, they stay the same, but the y values, x values change, right? And then dilation of 1/2, 1/2 x, 1/2 y, and whatever we wanted to do that. Okay, do they make them similar? Yes, they're similar. Right, explain the reason I said for number 3. All angle measures are the same, and distances between vertices, these are proportional to the scale. There we go. That's my answer for those. So there's that. Okay, let's see if the second part of this is any different from the first. Boring. And boring. Let's see, that was a rotation. And let's do that one in case it's being tricky. I'll do both of them. It'll take too long to do both. So at least. Write a sequence transformations for these. Well, first I need to see. These are all right angle. A little blurry, but that's all right. All right, so what is this? Is 4-1. This is 5-9. All right, and these are not the same. These are not okay because the distance between Q and R that is 3 units. And this is 4 units. So that's 3 to 4. That's 3. That's 3 to 4 units. This is 3 units over. 3 units over. This is 4 units over. And then the change over here is 2 units. This is 2 units down. I keep on writing 2. This is 2 units down. And this is 3 units down. So it's a 2 to 3 change. So 2 to 3 change here, 2 to 3 change here. So although the sides are all 90 degrees, they're not similar, right? So they're not similar because of that. So there's that. That's what I think at least. Let me look at the key and see what they have to say. E that is not E. That's correct. Okay. The sides are not proportional. That's what the answer says. The sides are not not proportional sides. That's what this said. Okay, so here we go here. So the write a sequence for transformations above, and let's see what they have to say here. Number 8. It's a tricky statement because you can't do that because this is a change in 2. What's a change in 1 for? So this is from Y to Z. That's a Y to Z change. That's too big. Drop it down to 1. So for change in 1 down, it's 4 over. Okay, so if we flipped it over, this would be a change in, what's a change in 2 down for a change in 1, 2, 3, 4, 5, 6. Right, so that is not the same proportion. So I mean, I could just flip this guy over right now, rotate it 90 degrees. Oh, I gotta select bigger, I guess. Rotate this thing 90 degrees. I'll tell you right now, maybe rotate it again 90 degrees. And then rotate it again 90 degrees. Again 90 degrees, okay. And I can tell you right now, these transparents, yeah, that these angles are probably not going to be the same. Yeah, they're not the same angles. Not even close to the same angle. I don't know if you can see that real well. I'll park it right there. But the old image is this. So this is the one image, and this is the other image. The angles are not the same. So they don't work. Don't work. The angles are not the same. So they are not proportional. If they were proportional, those angles would be right in the same lines. So it doesn't work. So they are not the same, and angles are dissimilar. Angles not same. Line segments not proportional. There you go. So there you go. That's how you do all that stuff. Pretty straightforward. Hope that helps out. And Zoom call. Here's the button to do that. So there it is. Okay. Guys have a great rest of the day.